be the best way to add audio-visual capabilities to a Jetson Orin Nano from NVIDIA?
For a mobile robot using a Jetson Orin Nano, you'll want hardware that balances performance with physical stability so things don't rattle loose while it's moving. 1. Vision, cameras. Since you're doing object detection, you'll want a CSI, camera serial interface camera, rather than a USB one.
What audio card I can use on the USB for both speaker and microphone?
I'm just hanging out and ready to help. For the Jetson Orin Nano, the most reliable plug-and-play USB option is the WaveShare USB audio coder. It's a tiny board that plugs right into a USB.
Does it support both speakers and microphones separately?
Yes, it definitely does. Both the WaveShare and the ReSpeaker options are designed to handle two-way communication. For the WaveShare USB audio card, you get a built-in microphone right on the board and a physical speaker header, a 2-pin connector, where you can plug in a small 8-ohm speaker. It also has a 3.
If I have Orin Nano, should I stick to a small language model or a large language model for robotic decisions like taking commands via audio and object detection and controlling motors?
Even with the Orin Nano, you should definitely stick to a small language model for those robotic tasks. While the Orin is a powerhouse for its size, running a large model would eat up almost all your memory and processing power, leaving nothing left for real-time object detection or motor control. Using a small language model like PHI-3 Mini or Tiny Llama allows the Jetson to multitask. It can listen to your voice, process the surroundings through the camera, and drive the motors all at once without lagging. In robotics, a fast response from a small model is much better than a slow, smart response from a huge one, especially if your robot is heading toward a wall. Would you like the terminal commands to see how much memory your current model is using while it runs?
I will add a dashboard and show in real time. Will adding a display be useful in such a scenario?
Adding a display to a mobile robot is incredibly useful, especially during the development phase. It acts as a window into the robot's brain. You can use it to show a real-time video feed with bounding boxes around objects the Jetson detects, or even display a console log showing exactly why the robot decided to turn or stop. Since the Orin Nano has a display port and supports high-speed interfaces, you could mount a small HDMI or dedicated touchscreen right on the chassis. This way, you don't have to lug a laptop around to see what's going wrong if it gets stuck or ignores a command. Just a heads up though, driving a high-resolution screen does use some GPU and memory. If you're pushing the limits with your vision and language models, you might want to stick to a smaller, lower-resolution display to keep the performance focused on the navigation tasks. Would you like to know how to monitor the system resources in real time to see if adding that display impacts your frame rate?
What would be the best resolution to keep the GPU to a limited capacity as you mentioned, but also be able to transmit it to a handheld unit within say 300 feet?
For a 300-foot wireless transmission while saving your GPU for the AI, you should target 640 by 480 VGA or even 480 by 320. Running at a higher resolution like 1080p will force the GPU to spend too many cycles just encoding the video stream, which will slow down your object detection and LLM. Lower resolutions significantly reduce the data load, which is critical because Wi-Fi signals can get pretty shaky at 300 feet, especially if there are obstacles. To make this work well over that distance, you'll want to use a compressed stream like H.264 or H.265. The Jetson has a dedicated hardware encoder for this, so it won't tax your main thinking cores as much as raw video would. Are you planning to stream this over a standard Wi-Fi router, or are you looking into a direct point-to-point radio link?
Direct point-to-point radio link. Do you have an adapter in mind?
For a 300-foot range on a mobile robot, you have two distinct best paths, depending on whether you want a dedicated networking bridge or a specialized robotics telemetry link. 1. The networking bridge, best for video plus dashboard. If you need to stream that VGA video feed and a web-based dashboard reliably, a Ubiquiti AirMax NanoStation Loco 5AC is the industry favorite. How it works: you mount one on the robot and one on your base station or a tripod. It creates a high-speed 5 GHz invisible Ethernet cable through the air. Why it's good: it handles high bandwidth easily, so your dashboard won't lag. It's much more stable than standard Wi-Fi at 300 feet. The setup: you'll need a PoE, Power over Ethernet injector to power the unit on the robot, which usually requires a 24-volt step-up converter if your robot runs on a 12-volt battery. 2. The robotics telemetry link, best for control plus small data. If you care more about sending move-forward commands and receiving text-based data from the LLM than seeing high-res video, look at the Holybro Microhard P900. How it works: this is a 900 MHz radio. Lower frequency means it can punch through walls or bushes much better than 5 GHz. Why it's good: it's tiny and plugs directly into the Jetson's serial UART pins. It's incredibly rugged and long-range by design. The trade-off: the bandwidth is lower, so streaming video will be much choppier compared to the Ubiquiti. 3. The hobbyist budget option. If you want something simpler, a high-gain USB Wi-Fi adapter with external antennas, like an Alpha AWUS036 ACM, can often hit 300 feet in an open field. You just plug it into the Jetson's USB port and point the antennas toward your handheld unit. Given that you're running an LLM and a real-time dashboard, the Ubiquiti NanoStation is likely your best bet because it provides the fat data pipe you'll need for the video and UI. Since you mentioned a handheld unit, are you planning to use a tablet or a dedicated controller with its own screen?
Before that, I'm using two NRF transceivers for GPS course correction and for communication between the handheld unit and the robot. I believe they operate at 2.4 GHz. Will there be interference?
If you are already using NRF24L01 transceivers for your GPS and basic telemetry, you have a solid foundation for low-power data, but there are a few things to keep in mind as you scale up to a mobile robot with an LLM and a dashboard. The NRF24L01 is fantastic for sending GPS coordinates and small motor commands because it uses very little power and the latency is quite low. However, its maximum data rate of 2 megabits per second is just not enough to handle a real-time video stream for your dashboard, even at a low VGA. Take it.
I'm not talking about using an RF for video transmission. I'm talking about interference between video transmission and the NRF. Is that an issue?
That is a very sharp observation. Interference is definitely a potential issue because both the NRF24L01 and standard Wi-Fi, which you'd likely use for the video dashboard, operate on the 2.4 GHz frequency band. If they are sitting right next to each other on a small robot frame, the stronger Wi-Fi signal can easily drown out the NRF pulses, leading to dropped GPS packets or laggy controls. To avoid this, you have a few solid options. First, you could switch your video transmission to the 5 GHz Wi-Fi band. Most modern high-gain adapters and bridge units like the Ubiquiti support 5 GHz, which lives in an entirely different neighborhood than the...
You also mentioned a 900 MHz transmitter for video. Will that be better for avoiding interference?
Switching the video to a 900 MHz link would definitely solve your interference problems with the NRF24L01 because they operate in completely different frequency neighborhoods. Since the NRF stays at 2.4 GHz and the video would be down at 900 MHz, they won't even notice each other. However, there is a catch. The 900 MHz band has much less room for data than 2.4 GHz or 5 GHz. While it's amazing at punching through walls and avoiding interference, you'll likely struggle to...
Will 900 MHz be enough for a 640 by 480 transmission?
It is a bit of a tight squeeze. At 640 by 480, you are looking at a lot of data for a 900 MHz link to handle smoothly. You would likely experience a very low frame rate, maybe only 5 to 10 frames per second, and significant lag. While it is great for avoiding interference and going through walls, the highway just isn't wide enough for a high-quality video dashboard. For a crisp real-time feed, 5 GHz is usually the way to go, even if it requires a clearer line of sight. Does that frame rate sound like it would work for your needs, or do you need a smoother video feed for driving the robot?
Switching gears now, I'm using a course correction for my RTK GPS. What is the latency provided by that system?
Since you're using the NRF modules for RTK course corrections, the 900 MHz option for video actually becomes a bit.
The question is, how much latency can I expect from that GPS correction?
When you're using NRF24L01 modules for RTK course corrections, the latency you can expect is generally very low, typically under 10 milliseconds for the radio transmission itself. This is well within the sweet spot for maintaining a centimeter level RTK fix. However, for your mobile robot, there are 3 types of latency that combine into your total delay. 1. Radio latency, approximately 1 to 5 milliseconds. This is how long it takes the NRF module to zip the data across the 300-foot gap. If you have auto-acknowledge turned on, it might jump to 15 to 20 milliseconds if it has to retry a packet due to interference. 2. Correction age, approximately 1 second. RTK base stations usually send out a burst of data, RTCM messages, once every second. This means your rover is often working with data that is aged by up to a full second, which is normal and handled by the GPS hardware. 3. Solution latency, approximately 20 to 100 milliseconds. This is the time it takes the GPS chip on your robot to actually crunch the numbers and output your coordinates to the Jetson. The danger zone. If your latency or correction age spikes above 2 seconds, your GPS will likely drop from a fixed status to float, and your accuracy will drift from centimeters to decimeters or even meters. To keep it tight, make sure your NRF modules are set to a high data rate, like 2 megabits per second, and that you've physically separated the antennas from your video transmitter. How much precision does your robot need for its specific task?
I need a centimeter level precision and I need it in under 1 second. What can I do to improve the speed?
To hit centimeter level precision consistently in under 1 second, you really need to focus on your RTK update rate and the age of differential. First, make sure your RTK base station and rover are both set to output at 5 Hz or 10 Hz rather than the standard 1 Hz. This forces the GPS to calculate the position solution much more frequently, which slashes your calculation latency. Second, since you're using NRF24L01 modules,
I have a NavSpark PX1122R RTK GPS. Does it allow 5 or 10 Hz correction?
the SparkFun SkyTrack PX1122R absolutely supports both 5 Hz and 10 Hz update rates. In fact, 10 Hz is its maximum capability for Quad-G NSS RTK. For your mobile robot, bumping it up to 10 Hz will significantly improve your real-time performance because the Jetson will receive a position update every.
Assuming I change it to 10 Hz, what would be end-to-end latency for the robot to receive the correction and then get the precise location?
At 10 Hz, your PX1122R is spitting out a fresh position every 100 milliseconds. If you've optimized your code and NRF modules, you can expect an end-to-end latency, from the moment the robot calculates a move command based on its current GPS fix, to the moment it verifies its new position, to be somewhere between 150 and 250 milliseconds. Here is the breakdown. The radio transmission and serial processing on the Jetson will take about 20 to 50 milliseconds. The internal processing of the GPS engine to provide that precise RTK solution adds about 100 milliseconds of age to the data. To keep this speed up, you really need to make sure you aren't using blocking code in your Python or C++ scripts on the Nano. Use asynchronous reading for the GPS serial port so the Jetson can keep thinking about the direction while the next coordinate packet is still flying through the air. Are you planning to write the control loop yourself, or are you using a library like MicroROS to handle the timing?
The GPS units are handling it themselves. I have a rover and a stationary unit for RTK. They communicate between themselves.
Since your hardware is handling the RTK injection directly, you are in a great spot because the Jetson Nano doesn't have to waste cycles processing the raw correction data. At 10 Hz, your biggest hurdle is just making sure the age of differential stays low. If your NRF link is solid, the robot will essentially be making decisions on position data that is only about 100 to 150 milliseconds old. To keep that speed consistent, you should check that your NRF modules are set to their highest data rate and that you've disabled any unnecessary NMEA strings on the PX1122R. You really only need the GGA and RMC strings for navigation. By stripping out the rest, you reduce the serial buffer lag on the Jetson side. Do you have a way to monitor the RTK fix status on your dashboard so you can see if the link drops while the robot is moving?
Not yet, but can the rover be configured to do this more quickly? I know we talked about the stationary unit.
Yes, you can definitely speed up the rover's side of the equation. Since the hardware is doing the heavy lifting, your goal is to reduce the buffer lag in the communication chain. You should set the rover's serial output port to a much higher baud rate, like 115,200 or even 230,400, to make sure the position data isn't waiting in a queue to get to the Jetson. Also, you can configure the PX1122R to only output the GNGGA message, which contains the RTK fix status and coordinates, while disabling all other unnecessary data strings. This keeps the data packet small and easy for your code to digest instantly. Are you planning to write a script to monitor the fix quality in real time?
No, I plan to configure it and leave it on the rover. I won't have bandwidth to monitor it continuously when it's running.
That is a smart move. To speed up the rover's internal logic, you should look into the Skytrack binary protocol instead of standard NMEA. NMEA is text-based and slow to parse, but the binary format is much leaner, which reduces the time the Jetson spends decoding the position. You can also set the NMEA precision to high and disable any talker IDs you do not need. Since you are configuring it yourself, making sure the rover's CPU is not stuck waiting on serial buffers is the biggest win for your 1-second goal. Are you planning to use a specific language like C++ to keep that parsing speed at its absolute maximum?
Not yet. My code is in Python.
Python is great for prototyping, but it can be a bit slower at parsing serial data if you're not careful. Since you're configuring the rover for maximum speed, make sure you're using the PySerial library with a small timeout and a high baud rate to keep things snappy. One trick to get that end-to-end latency down is to use a dedicated worker thread just for reading the GPS. This prevents your main logic, like the LLM or motor control, from pausing while waiting for a coordinate string to finish arriving. If the GPS is on its own thread, your main loop can just grab the latest position instantly whenever it needs to make a move. Since you're handling the configuration yourself, are you planning to use the binary format we talked about, or are you going to stick with the simplified NMEA strings?
The units are configured for NMEA for now, but I will look at the binary configuration. Can you note this entire conversation and send it on my Google account?
That is a solid plan. While you are sticking with NMEA for now, I will note that switching to the Skytrack binary protocol later is your ace in the hole for reducing latency even further. Binary is much more efficient because the Jetson does not have to spend time converting strings into numbers, it just reads the raw bytes. Since you are using Python, you might also look into the UBX transceiver or similar libraries when you make that jump, as they are built to handle binary GNSS data quickly. For now, just ensuring you have those high baud rates and minimal NMEA strings will get you very close to that sub-second response time. Are you ready to dive into the dashboard setup next, or do you want to verify the current GPS lag first?
No, I want you to note down this entire conversation on my Google account.
I can certainly help keep track of this for you. Since I can't directly save a text file to your Google account storage or a specific doc right now, I'll keep this conversation history in our chat log so you can access it anytime you need to reference these specs for the Orin Nano, the PX1122R configuration, or the radio links. Is there anything else you'd like to dive into before you start testing the GPS lag?
That was fun.